Welcome back to the Math Professors. If you enjoy content that can be found in any college math class, please consider liking, subscribing, and sharing. I'm Professor Van Hamlin, and I'm going to cover linearization and the relation to tangent lines today. So if f is a differentiable function at x equals a, then the approximating function L of x is equal to f of a plus f prime of a times x minus a. Now, what this is, this approximation function, is nothing more than the tangent line. That, this really is like if we look at a tangent line, just kind of force this. So if I say y is equal to m times x minus x1 plus y1, and actually let's even kind of go to like your normal point slope form. You usually see this, right? Y minus y1 is equal to m times x minus x1. So if I want to send that y1 to the other side, so we're going to have this. Now, instead of using x1, we use x1, which is equal to a. So now what we're going to have is an x minus a. Now your y1 is just the output of, the function at a, which really means it's just f of a. So this y1 is just plus f of a. And we know that the slope of the function is found by, the derivative at that particular a value. So m is just nothing more than f prime of a. So, simplifying this function, or really just putting the f of a in front, we can see that this is nothing more than the tangent line using the derivative. Now, what we say is that this linearization function is the linearization of f at a. So what we're trying to do is we're trying to approximate this particular function at a particular a value. And, the functions tend to be curves, or maybe something, some complicated curve, but what I can do is I can approximate it around the little tiny points using really a line. And what's nice about lines is really kind of like everything. They're very simple to work with. So this approximation says that f of x is really similar, or can be approximated by this L of x, or this tangent line, around this value of x is equal to a. Now, we also say a is going to be the center of this approximation. Now let's graphically kind of see what I'm talking about here. So what I've done is I've chosen this radical function, and I know that it's been shifted to the to the right one. So we know that this square root function is going to look something like this. Now what I want to do is I want to approximate this function around not 1 but around 2. So if I zoom into this function right here, what we can see is that I could look at its tangent line around this point here, and I can see that it looks like this. This thing right here is going to be our L of x. Is going to be the tangent line to this blue function at a equals 2. Now, if I zoom into this function, like the closer and closer we get, so what I'm going to do is I'm going to zoom way into this piece right here. So if I zoom in, what we can see is that, it's still a curve, with a particular tangent line. And then if I zoom in even more, what we can see is that this, it's going to look less curvy the closer and closer we get to this particular function. So what this allows me to do is if I get closer and, even closer, so, this one being the blue zoom, and then say this one being that yellow zoom, you can see the closer we get, the L of x, looks very, very similar to, f of x. So if I want to know values of, output values of this blue function, what I could do is I could find its linearization or its tangent line. And as long as I'm plugging numbers that are really close to, this center of 2, where I'm centered at, I'm going to get very similar outputs for the tangent line as I will for the blue curve. So let's find the, let's kind of verify this. So let's find the linearization of this particular function at 2, and we know they're going to share the same value at 2. because, you know, they intersect at 2. But what about like maybe 2.1 or maybe 2.01 and so on, or maybe even 1.9? We could actually look at their output values of, you know, of each one. So first, let's find this tangent line. So what I know, in order to find the tangent line, I'm going to need the derivative, and I'm also going to need the evaluation. I already know the x value, so I'm going to need to know f prime of that particular a. So I'm going to know f prime of x. So while this is equal to, you know, I'll write it over here and do some work. So f of x, I should do it in blue, f of x is equal to, you know, this is x minus 1 to the 1/2. So if I want to find its derivative, I can pull out that 1/2. And then it's going to be x minus 1 to the negative 1/2, multiplied by the derivative of what's inside, which is just, you know, 1. So this derivative is going to be 1 over 2 times the square root of x minus 1. Now, if I'm looking for its slope, I need to know f prime of a. In this case, is going to be f prime of my set a is equal to 2. So this is going to be 1 over 2 times the square root of 2 minus 1. So 2 minus 1 is 1, so the square root of 1 is 1. So this is just going to simplify to 1/2. So that's going to be the slope of this tangent line. I'm also going to need to know, you know, f of a. You know, I found f prime of a. I'm also going to have to find f of a. So f of a, you know, it's really just, remember, this really is the blue function. So this is the square root of, you know, 2 minus 1. And we know the square root of 2 minus 1 is going to be equal to just, you know, the square root of 1, which is going to be equal to 1. So finally, my L of x, my linear approximation, is going to be f of a, which is equal to 1, plus f prime of a, which is going to be 1/2, times, you know, x minus this a, which is going to be equal to 2. So that is the linear approximation to this blue function. And again, when we looked at that, it looks like this. This was that square root function, root x minus 1. And then this linearization at, remember, this is going to be at 2. This is going to be equal to that 1 plus 1/2 times x minus 2. Again, you can see if I plug in x equals 2, you're going to get the same value both times. But really, when we're trying to approximate this thing, I want to know what are the values really close to 2. So let's approximate it at, what's the approximation? At, say, x is equal to 2.1. Now, as long as I'm picking numbers that are really close to, say, this 2, and close, I know is not well defined, but we'll just say, you know, intuitively close. The output of this into this linearization should be very similar to the output of this into this blue function. Now, I know 2.1 is going to be right over here, so this is our 2.1. So the output in the linearization is going to be slightly bigger than the output into the blue function, so there'll be a little bit of error here, but we'll see, probably not much. So I'll just plug it in using a calculator. So into the function, so L of 2.1 is going to be 1 plus 1/2 times 2.1 minus 2. So this is going to be equal to 1 plus 1/2 times, you know, 0.1. So what I get is I get 1.05. 1.05. And I can also see, like, what would I get, you know, what is the function at 2? So let's see how close we are. What is how close we are if I plug this into the function? So we're going to do f of, you know, that exact same, you know, number. Instead of 2, we're trying 2.1. We're going to see how close we're going to get here and see how much error we have. So second square root of 2.1 minus 1. So we're going to get 1.048. So this gives us 1.048808. So this is good enough. So what I can see is that as long as I'm plugging in numbers that are close, we can see that these values really are not that much different. So if I was going to round to, 3 sig figs, it would round to the same number. And we could also do this for, I could say maybe 1.9 or maybe even like 1.99 or something if you wanted to figure out its approximation for that. We know it's still going to be slightly more, but again, you're going to see that the error is pretty daggone, small. So let's do another linearization to estimate a value for a particular function. So what I want to do is I want to find a linearization at a suitable chosen integer near this x value. So I'm given f of x, which is x over quantity x plus 1 at x equals 1.2, and I want to find the linear approximation. So we know that, the linear approximation is going to be equal to f of a plus f prime of a times x minus a. Now, I need to choose an a that is close to this given x value. So let's choose x is equal to 1. All right, so that means I'm going to have to fill this thing out. I need to know what is f of 1, what is f prime of 1, and so on. So f of 1 is going to be 1 over 1 plus 1. So this is going to be equal to a half. And I'm going to need to know f prime of 1, but f prime of x is going to be, well, I'm going to have the quotient rule. So derivative of the top times the bottom minus the top times the derivative of the bottom all over the bottom squared. So this is going to simplify to 1 over x plus 1 squared. Now plug it in, this value of 1. This is going to be 1 all over 1 plus 1 squared. So this is going to be 1 over 2 squared, or a fourth. So now I know that my linear approximation can be done by this. L of x is going to be equal to f of 1, which is going to be a half, plus f prime of 1, which is going to be equal to a fourth, multiplied by x minus this a value again, which is 1. I should have said instead of x equals 1, we should have said a is equal to 1. Boom. There we go. Okay, so that's our linear approximation, and I want to figure out, basically I'm trying to figure out the value of this thing at 1.2 using the linear approximation instead. So as long as this a value is close to this, the output of this should be very similar to the output of this. So let's see what we have here. So what is L of 1.2? Well, this would be 1/2 plus 1/4 times 1.2 minus 1. So this is 1/2 plus 1/4 of 0.2. Let's see what we get here. So what I get is 0.55. And I'm kind of curious how close we got to f. So let's plug this into f as well, and just to kind of be sure that that things are looking good. So remember that this is going to be, we're plugging in our 1.2, so this is a 1.2 all over 1.2 plus 1. So 1.2 divided by the quantity, 2.2. So what I get is 0.545454 repeating. So this gives us 0.5454 and so on repeating. And what we can see is, again, these outputs are really close, as it should be. And let's do one more linearization. Let's pick a trig function. I'm just going to find the linearization for this and not really estimate any values. So let's just go ahead and find L of x. All right, so here's our last example. I want to determine the linearization of f of x, which is equal to the tangent x, at a is equal to 0. Now, graphically, what we know is our tangent function looks like, it's got asymptotes at negative pi over 2 and positive pi over 2, so it's going to look something like, something like this. I'm choosing this because it's a relatively famous one that we linearize all the time, and I know that my linearization should be, should be this tangent line right here. That should be equal to L of x. So in order to find L of x, we know that this is going to be equal to f of a plus f prime of a all times x minus a. So a in this case is equal to 0, so I'm going to need to know what is f of 0. So f of 0 is going to be equal to the tangent of 0, and the tangent of 0 we know is going to be equal to 0. It goes right through 0, 0. I'm also going to need to know f prime of a, but before I find f prime of 0, I'm going to have to find f prime first. So the derivative of the tangent is going to be equal to the secant squared of x. So that means f prime of 0 is going to be equal to the secant squared of 0. Now, this is 1 over the cosine squared of 0. And the cosine of 0 is equal to 1, so this is 1 over 1 squared, which is equal to 1. So now I know that L of x is going to be equal to f of 0, which is 0, plus f prime of 0, which is equal to 1, multiplied by x minus 0, because that's what a is, x minus 0. So this just spits out the function x. So this is our linearization, which is just y is equal to x of that tangent function. So if you like the content, please subscribe.